Right, this is 10.3 reaction mechanisms. There was 3 concepts that we learned in 10.3. Go through them one by one. The first concept is that reactions occur through a series of elementary steps that together form an overall net equation. Now, this idea of elementary steps we haven't learned yet, so let's try to figure that out. What we have seen so far in chemistry is we've seen overall net equations. We didn't know that they're overall or net equations, we just thought they were equations. So for example, something like H2 plus 2ICl yields I2 plus 2HCl, right? We learned how to write those in Unit 6, and we've been working with them, and that's what chemistry is all about, and we're familiar with this. What we haven't known, though, is that behind the scenes, there are a number of steps, actually, behind this, that, in order to do this, really, the 2 steps had to occur, and that this is just the overall net. It's kind of like this. You go to a movie theater, right? Or sorry, theater for like plays and musicals, right? And you see the play and the musical, right? And that's what you can see on the surface. But behind the scenes, right, there's so many other things, right? There's the lighting crew, there's the tech crew, there's the costume, the makeup, right? The directors, right? There's so much else that goes into it. We see this, but what's happening is these steps are happening below the surface. And so step 1 is we do H2 plus ICl, and that yields HI plus HCl. And then what happens is that HI then gets combined with another ICl to make I2 and HCl. And so overall, net, what we create, right, is we do this, and we can see that here, right? If we add these 2 steps together, because that's what we're doing, right? We're doing this, then we're doing this, so we can add them together. What we're doing is you have H2 plus ICl plus HI makes I2 plus HI plus HCl plus HCl. Now do note, right, that if I have 2 ICLs, right, that's 2 ICl, right? 2 ICLs are 2 ICl, and 2 HCl's are 2 HCl's, or 2 HCl. And so if you think I'm saying the same thing, I am, right? That's the point. 2 ICl is 2 ICl, and then we have HI yields I2 plus 2 HCl plus HI. Now the last thing we can see here is that also HI is both on the left and the right, and so we don't actually need it, right? We can just say, right, you can just cancel it. Think about it in terms of like math, right? If you have like, I don't know, 5x plus 3 is equal to, let's use 7x plus 3. Right? Ultimately, if we're simplifying this, right, we can just do minus 3, we do it on both sides, and so you just get 5x is equal to 7, right? There's plus 3 on both sides, right? It gets canceled. And so, and it's the same thing here, right? And so overall, this is our equation. And oh, look, that's the same thing, right? Yeah, that's the whole point. This equation that we see is really made up of these 2 elementary steps, which when we add them together, form that overall net equation. And so that's the first concept we learned, this overall idea. Second concept is that the number and type of elementary steps are what determine the speed of reaction. So in the same way that we were saying, like, hey, you come to a theater performance and you see the performance itself, right? What ultimately determines the quality of that performance is all the stuff, all the behind the scene things. And so here, if we can understand molecularity, energy of the step, and the number of steps, we'll understand what determines the speed of a reaction. And so molecularity is simply referring to the number of molecules or particles that are involved in that elementary step. And so basically, you could have unimolecular, where you have just 1 molecule involved. And that's, for example, if you have decomposition, right? It's like, hey, we have this thing where there's like 3 atoms, right? But 1 molecule, and it'll break up into like something like this, right? That's unimolecular, right? There's only 1 molecule involved there. And so that's unimolecular. You could also have bimolecular, which is when you have 2 molecules, or particles, technically, it could be atoms, involved. And then lastly, you can have trimolecular, where we have, take a wild guess, 3 molecules or particles involved, right? And so I didn't have enough room to draw these out, right? But bimolecular, right, it's like, okay, you might have 2 molecules, right? Maybe this one has 2 things, this one has 1, right? And they come together, and then they form, as a result of it, something with 3. Or trimolecular, if you have, let's say, something with 2, something with something else with 2, and let's just say something else with 2, right? They come together, and as a result, they form this new 6 atoms, but 1 molecule structure, right? And so this is molecularity. Now, the point is that this is very slow, and this is very fast. Unimolecular is very fast, and trimolecular is very slow, right? Because of probability. Basically, the probability of 3 things hitting each other with the right energy and the right orientation is very unlikely, right? It's very unlikely for that to occur. Whereas for 1 molecule, it's very easy for that to occur. It's very easy for it to coordinate that, right? You could think about our relay race, right? When you had just 1 person involved, it was very easy. When you have 3 people involved, it becomes very difficult to coordinate your feed and everything, right? Another way to think about it is the probability of you going to In-N-Out at 7 p.m. on a Wednesday. If you really like In-N-Out, right, the probability that you're there at 7 p.m. on a Wednesday, it's actually kind of low, right? Because if you think about it, 7 p.m. on a Wednesday exactly, like, it's like, okay, I'll go to In-N-Out like maybe once a week, but still, like, 7 p.m. on a Wednesday exactly, that's hard to coordinate. But still, right, the chances aren't bad, especially if you're like In-N-Out. But how about this? What's the chances of you and your friend, uncoordinated, both ending up at In-N-Out at 7 p.m. on a Wednesday? Right? The chances of that are very low, right? Because the chances of 2 people being in the same place at the same time are very low. And the same thing with bimolecular. The chances of 2 molecules or particles being in the same place and thus colliding in the right way with the right energy is very low. Trimolecular is even worse, right? Think about it. What's the chances of you, a friend, and then another friend all ending up at In-N-Out at the same time, 7 p.m. on a Wednesday, right? That's very unlikely. And so trimolecular reactions are very difficult. It's going to take a long time for them to occur because the probability of it happening is just very low, right? So that's molecularity. If any of your elementary steps have, or trimolecular, that reaction is going to be so slow because of that trimolecular step. The second thing is the energy of the steps, right? Some steps require a lot of energy. And so if you have a reaction where it's like you have a big activation energy, that's going to be slow. Whereas if you have a reaction step that has very low activation energy, right? And this one, let's make it, actually, let's stay with exothermics so you don't get confused, right? This one is going to be fast, right? It's easy to get this much energy. It's much harder. It's going to take a long time to get that amount of energy. And so energy steps is going to be important. And then lastly, the number of steps is also important. Basically, right, it's common sense. If you have 6 steps you have to go through, it's going to take a long time for that reaction to occur. Whereas if you only have 2 steps, the reaction is going to go faster, right? I don't have to write anything. Sorry. I don't have to write anything below here, right? 6 steps, slow. 2 steps, fast, right? So the number and type of elementary steps determine the speed of our reaction. That was the second concept. And then we just did some practice of how to get an overall net equation from our reaction steps. And here's the basic idea. We did it here, right? Just add the steps together and cancel things that are both on the left and on the right. And so let me do an example for you guys of that. Let's take a look here, right? This was actually from our a little packet handout that I give you guys, right? And so O3 yields O2 plus O, and then O3 plus O yields 2O2. The basic way to do this is to say, okay, well, I'm going to have everything here add up together, and then everything that's both on the left and the right, I'm going to cancel them. And so we have 2O3 plus O yields O2 plus O plus 2O2. And so what we see is that on the left and on the right, we both have O, and so we can cancel those. And so now we have 2O3 yields 3O2. And so that is our overall chemical reaction, overall equation. Now do note, another way of doing it, right, and kind of the way I do it, is I'm just like, okay, well, I do that. So now I have 2O3, 3O2, and then I just add them together. So for me, just like, once I cancel, I'm like 2O3 plus 2 plus 1 plus 2 is 3O2. And so I do it like that. You can do it either way you want. The point is just cancel what's on the left and the right. Yeah. Do you know what the name of this thingy is, right? This guy? Right? This is an intermediate, right? Because it's something that's created and then immediately destroyed. And so it doesn't ask you for that, but O is an intermediate, and we remember that from our packet. And so that's how you do that. That's how you get an overall net equation. And so hopefully that helps. Do your practice problems. Let me know if you have any questions. You got this test next week. You're going to do great.